Thanks for tuning into the FORC talk on outcome indistinguishability. This is joint work with Cynthia Dwork, Omer Reingold, Guy Rothblum, and Yona. In this work, we revisit the underlying goals of individual risk prediction. Typically, the goal of prediction is framed as finding a best fit hypothesis. For instance, the agnostic pack model formalizes the goal by first fixing a hypothesis class, and then learning a hypothesis H that achieves loss, in this case, the squared loss, that competes with the best hypothesis in the class. While this framework has been wildly successful for learning accurate predictors across many different domains, a critical downside of the pack framework is that it only considers the overall performance, and it doesn't make any requirements on where errors occur. For instance, they could be concentrated on an important subpopulation, which could lead to downstream unfairness. And really, in this framework here, fairness is viewed as a constraint. So any attempt to improve fairness must be traded off with accuracy. So in this work, we propose a new paradigm for learning, outcome indistinguishability, that frames the goal of learning as finding a model that in some sense is indistinguishable from the true outcome model, which we'll call nature. So to understand the goal, consider the following challenge. On the left-hand side, we'll take an individual outcome sample, either from nature or from our model of nature. Then we'll pass this sample over to a distinguisher. Now, the distinguisher's job is to guess whether the individual outcome pair came from nature or from our model of nature. And intuitively, we'll say that it's indistinguishable if they can't tell. So the goal will be to develop a model where the distinguisher can't succeed much better than random guessing. More formally, we assume that nature is a joint distribution over individual outcome pairs, but we make no further assumptions. For the model of nature, we observe that any predictor, which we'll call p tilde, actually suggests a generative model for outcomes. In this distribution, we first sample an individual from nature, and then we resample their outcome according to the Bernoulli distribution with parameter p tilde of x, so according to their predicted probability. So with this notation in place, we can restate our goal to learn a predictor p tilde whose model distribution, dp tilde, is indistinguishable from nature's distribution. The question we have to ask ourselves then is indistinguishable to whom, right? So in particular, if we allow any distinguisher, then it's not hard to see that the model distribution must actually be statistically close to nature, which is impossible from a small sample. Thus, to have any hope of achieving this goal, we need to consider some sort of relaxation, and we'll consider a computational relaxation. Which leads us to our formal definition of the OI framework. So first, we fix some bounded class of distinguisher algorithms, which we'll denote A. Now, these algorithms map individual outcome pairs or individual outcome prediction triples to 0, 1. Good. And so with that, we say that a predictor is A epsilon OI if for all algorithms in the class, the probability that the distinguisher returns 1 on samples from nature and on samples from the model are within epsilon of one another. And so in this definition, note that in both cases, whether we're sampling from nature or from the model distribution, we only allow the distinguisher to look at the prediction according to p tilde, not according to nature. In the paper, we explore variants of this definition, and we'll get into some of them next. So before moving on, I'd like to draw a pretty direct analogy between the classic notion of computational indistinguishability and our new notion of outcome indistinguishability. Computational indistinguishability is widely used throughout cryptography and pseudorandomness. And really here, the classic perspective is somehow that randomness is in the eye of the beholder. In OI, we're suggesting that perhaps when thinking about individual risk, individual probabilities are in the eye of the beholder. And the goal really should be to learn simple generative models that somehow look like nature for all intents and purposes. Good. So earlier I presented the definition of OI as some fixed definition. In fact, we introduce a number of variants of OI. And each of these different variants is based on the distinguisher's access to the predictor P tilde. So in the first level, which we call no access OI, the distinguishers only receive individual outcome pairs. They don't receive any access to the predicted value, P tilde of X. Sample access OI is the next level, which I presented on the previous slide, where the prediction is also given on the sampled individual. So in addition to receiving X and Y, the distinguishers receive P tilde of X. Finally, in today's talk, we'll present a model called Oracle Access OI, where the distinguishers are allowed black box query access to P tilde. So they receive an input X and Y and must make decisions about X and Y and whether to accept or reject. But they're allowed to query P tilde, not just on X, but on any individual that they'd like. Good. And so note importantly, again, the only access to nature is through the outcomes. So we never see anything other than an outcome from nature. This aspect is the namesake of the term outcome indistinguishability, and it's important. In the paper, we explore a few other variants of indistinguishability, exploring their properties and desiderata as desiderata for learning, but argue formally why OI is the one that makes the most sense. Good. So one of our main results shows a strong connection between OI and the evidence-based fairness framework. So this framework for fairness takes the perspective that the first thing for a predictor to do is understand the evidence at hand and to reflect it as well as possible, using the statistical and computational resources available, not just on the overall population, but also when restricting our attention to structured subpopulations. For instance, the main notion, multi-calibration, aims to ensure well-calibrated predictions across computationally identifiable subpopulations. And so I have the definitions of both multi-accuracy and multi-calibration here. Feel free to pause and stare at them if you haven't seen them before. Good. So our first result demonstrates a tight connection between OI and multi-calibration and multi-accuracy, actually. So specifically, we show a computational equivalence between notions at each of the first two levels. So specifically, no access OI is equivalent to multi-accuracy, and sample access OI is equivalent to multi-calibration. And when I say equivalent here, I mean sort of computational or reduction-based equivalence. That's to say that for any class of subpopulations you give me, C, I can turn this class into a distinguisher class, a class of distinguisher algorithms A, such that enforcing AOI will imply C multi-calibration or multi-accuracy in the case of no access OI. And vice versa. The complexity of this reduction is very minimal. So really the distinguishers and the subpopulations, in a sense, are have the same complexity. Good. So what does this mean? The upshot of this is that the equivalence gives us algorithms for obtaining OI kind of off the shelf, just by appealing to the learning algorithms that already exist for multi-calibrated predictors. For instance, we can show that the complexity needed to implement OI predictors at the first two levels scales linearly with the complexity of the distinguisher class and polynomially with the accuracy parameter. So really, this does follow as a corollary of the reduction, But we can also show it more directly. And in doing so, we're able to generalize the results from multi-calibration, showing how to obtain OI predictors for all variants of the distinguishers that we consider, so at each of the levels. And again, the theorem is constructive. We prove the feasibility of OI by demonstrating a boosting style learning algorithm. And the algorithm works from a small set of samples, so it's statistically efficient. And you can view it as oracle efficient. That is to say that it can be implemented computationally efficiently if you can solve some certain agnostic learning problem. Good. So looking at this theorem statement a little bit further, I want to emphasize that the construction holds for any choice of nature. That is, for even arbitrarily complex natures, we can upper bound the complexity necessary to generate indistinguishable outcomes for each level of the distinguishers. Note, however, though, that once we allow the distinguishers to query the predictive model itself, once we allow oracle access, our upper bound no longer is polynomial in 1 over epsilon squared. It looks quite inefficient. So specifically, the complexity of the OI predictors that we can construct scale exponentially in the desired accuracy parameter. And so a really natural question to ask then is whether this inefficiency is showing up because we were lazy and just didn't find the best construction, or if there's something else going on here. And so in fact, it looks like we weren't just lazy. It looks as though this inefficiency for Oracle Access OI at the level that we study it is inherent. So specifically, we showed that under fairly weak fine-grained complexity assumptions, some exponential dependence on the accuracy parameter is unavoidable. That is, we construct a choice of nature and a choice of Oracle Access distinguishers A, such that any predictor that achieves A epsilon OI with this Oracle access requires complexity that scales exponentially in the accuracy parameter epsilon. And this is under a certain variant of the K-Clique conjecture, for those who are interested. Good. So at a very high level, the lower bound follows by constructing this nature and class of Oracle access distinguishers such that computing the outcome of an individual according to nature is based on a hard computational problem. So just if you wanted to compute nature exactly, it's hard. But what we'll show is how to construct an Oracle access class of distinguishers that can sort of run a self-reduction in this computationally hard problem, such that if you are able to achieve AOI, then the model must essentially compute this hard problem correctly. So collectively, this shows that implementing a predictor that achieves AOI must actually be computationally intensive. Good. So what I want you to take away from this talk, though, is that somehow Oracle Access gives us a qualitatively different kind of indistinguishability, that the Oracle Access distinguishers are very powerful, and that this query access allows the distinguishers to run these powerful tests much more efficiently than they would without Oracle Access. So again, to build intuition, the distinguishers can kind of check correlations in the outcome of various different individuals. And another way to say it is that using local checks, by probing in a few spots, they can enforce some global consistency. So how should you interpret this lower bound against Oracle Access OI? To me, what it says is that at the level of generality that we're working, that we study this problem at, the construction is roughly optimal. That said, it leaves open the possibility that on much more structured instances, Oracle Access OI may be achieved efficiently. And I think this is a really interesting open question to come up with very natural and well-motivated structured instances where you might be able to achieve Oracle access OI. Good. So the separation that we show really shows that this lower bound shows that this variant of OI with Oracle access is strictly stronger than other variants of OI, and thus is stronger than multi-calibration. And so a practical takeaway of this result is that in the real world, auditors should be granted query access to predictive models, not just predictions on historical data. So in other words, we're saying that somehow these Oracle access distinguishers are really powerful, then we should use them in practice. There's no reason to tie our hands. Good. So to recap, in this talk, I've talked about outcome indistinguishability and introduced it as a new goal for individual risk prediction. We saw a hierarchy of variants of OI and saw that when we allowed these distinguishers Oracle access to the predictor, we ended up with a qualitatively different notion of indistinguishability. And we discuss a number of further aspects in the paper. I want to conclude with a final discussion point where OI really aims to generalize this work on multi-group fairness notions, starting with multi-calibration, but really hoping to generalize all of these types of subgroup fairness notions. And so one intriguing idea is to think about that perhaps we can think of a fair predictor as somehow being indistinguishable from an ideal predictor. So if the ideal is really given by nature's model, then OI, as we've defined it, kind of already achieves this. But nature and the samples that we have access to isn't always the ideal. So I think it's quite interesting to see if we can figure out how to make this kind of intuition rigorous, that somehow if the ideal is a different distribution, what would it mean to be indistinguishable to that distribution? And how might one learn such a predictor? More than anything, I'd say that our main contribution is really setting up this framework. There are many open questions and possible extensions, and I hope that some of you will help us solve them. Thanks for your attention.